Hello, I'm Arik, and in this video, I'll overview our recent work on constrained hierarchical Monte Carlo belief state planning. Safe planning under uncertainty can be naturally modeled with constrained partially observable Markov decision processes, or CPOMDPs. CPOMDPs model problems that exhibit both outcome and state uncertainty. Outcome uncertainty describes uncertainty which may arise from things like imperfect actuation, environmental randomness, or actions of other agents. While state uncertainty arises from imperfect information coming from, for example, noisy sensors, occlusions, or uncertainty in the intent of others. An optimal constrained POMDP policy maximizes expected cumulative reward while satisfying hard cost constraints under, again, both outcome and state uncertainty. Solving CPOMDPs is really difficult, especially in large state action or observation spaces, which are common in many robotic domains. Recent work in CPOMDPs with large or continuous spaces used Lagrangian Monte Carlo tree search. To guide search towards constraint satisfaction, they would combine optimistic Lagrangian exploration with dual ascent to optimize dual variables, lambda of the Lagrangian. Then to scale to continuous spaces, they used a technique called progressive widening to artificially limit the branching factor of the search tree across actions and resulting belief transitions. And what this would do is this would sample more child nodes only as the number of visits to parent nodes increases. So to avoid oversampling of maybe unnecessary parts of the search space to explore. Now, the problem with this is that in many CPOMDP domains, even simple ones, they require deep searches. And this could lead to an exponential blowup in the number of possible trajectories. This is often called the curse of history. In this work, we introduced constrained options belief tree search, or COBETS. COBETS builds on top of Monte Carlo CPOMDP planning to address this tree blowup by planning over a hierarchy. COBETS plans over options or macro actions / low-level controllers, which are often available in robotic domains. In its search, COBETS would imagine the resulting particle filter from different possible option execution sequences, so from seeing different observations along the way during execution of these high-level options. And importantly, it would use progressive widening to limit the number of these sampled, now semi-Markov belief transitions. Semi-Markov here meaning it can the options can terminate after one or many or different numbers of time steps. So it would need to do this so that it could plan to long time horizons. So to see why this is useful, consider the light-dark CPOMDP. In this problem, an agent starts with high uncertainty in its position and must move in small, medium, or large steps to localize itself in a light region here before heading back to a goal, and must do this all without overshooting and entering this constrained region in red. A good policy will take medium and then small steps until the robot is safely localized, and then quickly navigate to the goal with big steps. However, because of the curse of history, finding the correct depth 7 action sequence, even if only sampling 1 or 2 observations, would require searching a billion trajectories. With COBETS, we can really get away with planning over options that either go to goal by greedily navigating from the mean state of the belief, and then options that use different strategies to localize. So in the search itself, for example, we might imagine the possible results of taking these different localization options and receiving different sample observations to plan accordingly. Now, in practice, we don't know what localized should look like, but we can template different localization options, for example, to different uncertainties or with different considerations of the constraint, and have safe search overcome this and pick the best one to execute, which might, say, end up choosing localization option B to run the best safe localization before going to the goal. Now, in our experiments, we demonstrated that COBETS scales CPOMDP planning on 4 constrained domains with large or continuous state action or observation spaces. In the spill point domain shown on the left, it's based on a carbon sequestration problem. where one has to inject carbon into a subsurface with uncertain geometry and features while making sure that there is no leakage back to the surface. So this problem requires choosing an injection point very early on, and it requires therefore making a very deep search over a large belief space to do well. In our robotic domains, shown on the right, an agent has to get to a goal region while avoiding a penalty region, all while avoiding the constraint of this hard constraint region in red. And here again, it doesn't know its starting position. It starts off with uncertainty over its state, as shown with the particle filter set in blue. We see that COBETS significantly outperforms state-of-the-art non-hierarchical CPOMDP baselines, which cannot plan on robotic domains because they require search of depth 50. In our constrained bumper Roomba domain, for example, COBETS is able to plan to find the correct sequence of belief-based options to first localize itself with those 2 bumps there before navigating to the goal while avoiding that constraint region successfully. COBETS also has a nice property where we can track the remaining cost to go along our search and assign it to options. And we show that with this, we show that if options are feasible, that is, that if they're able to satisfy the cost budgets assigned to them, that COBETS is guaranteed to satisfy constraints anytime, which is a very desirable property. So for example, if options themselves were trajectory optimization procedures, we could pass in the remaining cost budgets and ensure that our solutions satisfy constraints independent of the number of search queries. So we see this in our light dark problem where as we sample all the way down to 10 samples in our tree search, when using feasible options here, we have that COBETS is able to stay safe in an anytime fashion, while non-hierarchical baselines are not able to satisfy this constraint. Finally, we demonstrate that the reduction in tree size from hierarchical decomposition allows for COBETS to search over many options while coming up with good plans, even many more options than underlying action. So for example, in light dark, we're able to plan over 30 different multi-step options and get better safe performance than planning over the 7 single-step low-level options in the non-hierarchical baselines. And I think this is really exciting because it motivates future work that could auto-generate many options, for example, by prompting large language models, and use COBETS to choose the best ones to plan safely. Thank you.